Have you ever just watched a robot arm move and it's kind of mesmerizing? Or seen a CNC machine carving something out with just perfect accuracy? You've probably wondered, how in the world does it do that? Well, the answer isn't just a strong motor. It's actually a super fast conversation that's happening inside the machine, and we're going to break down exactly how it works. So yeah, that's the big question, right? How do you tell a machine not just to move, but to go to an exact spot at an exact speed and just stay there, no matter what? The secret is something we call a servomotor. But here's the crazy part. The servo magic isn't really the motor itself. It's the entire system that's built around it, because that's the first thing you've got to get. The real genius here isn't in the motor. It's in the whole ecosystem it lives in. And this quote, man, it just nails it. A servo isn't a specific type of motor, like AC or DC. Servo really just describes the job the motor is doing. It can be any motor as long as it's part of a very special system, a closed-loop control system. And that system, that's the real star of the show. Okay, so the fancy official name for this whole setup is a servo mechanism. And the best way to think about it is like you're trying to park your car perfectly. You're constantly glancing in your mirrors, right? You're checking the painted lines. You're thinking, where am I versus where do I need to be? Well, a servo mechanism does that exact same thing, but thousands of times a second. It's relentlessly trying to close that gap. This is the absolute core of how they get that amazing precision. All right, so to really get this servo mechanism thing, let's break it down into 3 simple ideas. Just think of it like it has brains, muscle, and senses. And here's a peek inside a typical one. You can see it's all packed in there. The electric motor, gears to give it some oomph, a sensor, and that little circuit board. Every single part has a vital role to play. Let's see how they fit our little analogy. So the muscle is easy. That's the motor itself. It does all the heavy lifting. The senses, this part is really cool. That comes from an encoder. An encoder is basically like a tiny, super high-resolution ruler that's constantly telling the brains the motor's exact position and speed. And then you have the brains. That's the control circuit, or what we usually call the servo drive. This is the boss. It gets the main order, listens to what the senses are saying, and then tells the muscle exactly what to do next. And it's that constant conversation between the brains, the senses, and the muscle. That's where all the magic happens. The whole concept is called feedback, and it's what makes the system so unbelievably smart. We call this cycle closed-loop control. Now, a simple system is open loop. It's like you throw a ball with your eyes closed and just hope it hits the target. But a closed-loop system is always watching. It sends a command, it measures what actually happened, it calculates the difference, which we call the error, and then it immediately sends a correction. And this loop is running hundreds, even thousands of times every single second. It's always hunting for zero error. This diagram lays it out perfectly. You've got the command value coming in, that's where you want to be. Then the system senses, the encoder, give you the current value. That's where you actually are. The brains simply subtract one from the other, and what's left is the error. And I'm telling you, that error signal is the most important piece of information in this entire system. And we got to be really clear about this. Error doesn't mean something went wrong. It's not a mistake. It's actually the instruction. If the error is a big number, it's telling the motor, hey, you're way off, move fast. If it's a tiny number, it's saying, okay, easy does it, you're almost there. And if the error is 0, that means you've arrived. Now hold your position. The entire goal of the system is to make that error number 0. Okay, so let's dive a little deeper into the brains of this operation. To get that mind-blowing precision, the servo drive doesn't just calculate one error. It actually uses a cascade of 3 loops, all nested inside each other, where each one refines the command for the next. Now, this diagram looks a little intense, but it's pretty straightforward. It all starts with a position command on the far left, and it ends with a motor turning on the right. Everything in between is our 3 loops, the position loop, the speed loop, and the current loop. Let's walk through what each one is doing. So the first and outermost loop is the position loop. It calculates the position error and figures out, say, we're 1,000 encoder pulses away from our target. But it doesn't just tell the motor to move. Instead, it converts that distance into a speed command for the next loop. This makes for a nice, smooth movement. So now the speed loop gets that speed command, compares it to the motor's actual speed, and then it outputs a torque command, which is basically how much muscle the motor needs to use. Finally, that command goes to the innermost current loop, which makes sure the exact right amount of electricity flows to the motor to generate that precise amount of torque. It's really a beautiful cascade. It takes one simple command, go to the spot, and turns it into this incredibly detailed set of instructions covering position, speed, and torque. It's how the motor gets to the right place, not just accurately, but also smoothly and with the perfect amount of force. Now, the physical piece of hardware that does all this thinking and also powers the motor is the servo amplifier, or what pretty much everyone just calls the drive. This is the box that takes in regular old wall power, listens to those low voltage commands, and transforms it all into the high power, perfectly controlled electricity the motor needs. Inside that drive, there's a 3-step power makeover going on. First, a part called the converter takes the AC power from your outlet and turns it into DC power. Next, a smoothing circuit cleans up that DC because it can be a little rough and creates a nice, stable power source. And then comes the real workhorse, the inverter. Think of it as a bunch of super fast switches. It chops up that clean DC power and rebuilds it into a brand new, custom-made AC signal. By controlling the frequency of this new AC power, the drive has total control over the motor's speed and torque. So you might be thinking, wow, that seems really complicated. And it is. So why do we go through all this trouble? Well, it all comes down to one massive advantage: feedback. Let's put our servo system up against a simpler open-loop system, like a stepper motor. A stepper motor just moves a certain number of steps and just assumes it got there. It has zero feedback. If it gets bumped or the load is too heavy, it can stall and lose its position, and it will have no idea it messed up. A servo, though? A servo always knows. It feels the resistance. It sees the position error growing, and those control loops instantly tell it to use more torque to get back on track. It's the difference between flying blind and having pinpoint vision. And that's really the key takeaway here. The power of a servo system isn't just about its strength or its speed. It's about its intelligence. It's the ability to see and correct its own errors in real time. That's what makes all of our modern, high-speed, high-precision automation possible. I mean, this quote really sums it up. When the stakes are high, when you absolutely have to be precise and there's no room for error, a closed-loop system is the only way to go. It's the gold standard for a reason. So the next time you see a machine moving with what looks like impossible precision, you'll know the secret. It's not just a motor. It's a smart, self-correcting system that's in a constant conversation with itself. Which leaves us with a pretty cool question to think about. With control systems that can already see and fix their own mistakes this fast, what incredible things will machines be able to do next?
Thanks for watching. Please visit the channel for such more content, and don't forget to subscribe the channel and like if it is helpful to your knowledge, and comment if something is wrong.